Hi there, welcome to the first video of my end-to-end project series. So let's see the code. So this is our project, visa prediction project, and this is the first video. So we are going to first do some EDA, then the feature engineering and model training on our IPYNB notebooks. Okay, and after that we are going to see the whole deployment, all the components like ingestion, validation, transformation, etc., all the components we are going to do for the deployment. Okay, so let's see. So this is our visa prediction project. So the life cycle of machine learning project, as you can see, is understanding the problem statement, data collection, EDA, data cleaning, data pre-processing, model training, and choosing of the best model. So we are going to see all of these in this video. Okay. So the let me zoom in. Okay. Yeah. So as you can see, the Immigration and Nationality Act of US permits foreign workers to come to US to work either on a temporary or permanent basis. The Act also protects US workers against the adverse impacts of working place, etc., etc., etc. Okay, the immigration program are administered by uh, OFLC, Office of Foreign Labor and Certification. So our problem statement is that OFLC gives job certification application for employers seeking to bring foreign workers in US and grant certification. So last year the count of employees were huge, so OFLC needs machine learning models to shortlist visa applicants based on their previous data. So this is our problem statement. We want to create a machine learning model which can predict whether to approve a visa or not uh, for OFLC. Okay. So in this project we are going to use a classification model to check if visa gets approved or not based on given data and recommend a suitable profile for application for whom the visa should be certified or denied, okay, based on certain criteria. So first data collection part, our data is part of OFLC. It consists of 25480 rows and 12 columns. Okay, let me see. Okay, recording is on. Yeah, so first let's import our libraries. Then we are getting our data set. So our uh, data set is there with the notebooks here, as you can see, in the notebooks folder of our main project folder. Okay, inside our main project folder, there is notebooks folder. There we have this file and the data set. Okay, so this is df head. So this is our data. Case ID. This is continent, from which continent the applicant is, education of employee, high school, master, bachelor, etc. Has job experience or no, yes or no, requires job training, yes or no, number of employees. This is the number of employees in the company that the applicant is going to work. This is the year of establishment of that company, region of employment, west, north, east, south, okay, etc. Prevailing wage. So what is the wage? Unit of wage. So is it hourly or yearly or monthly? Okay, this wage. So full-time position, yes or no. And this is our final target column, which is case status, which is denied or certified. Okay, so data set is clear. This is the shape. Now these are the 50th percentile, as you can see, 25 and 75. And we are checking the types. So all these are objects, okay, and this int and int, these are numerical features, okay. These are also objects, and this is also a numerical feature, prevailing wage. So now let's start the exploration process of our data. So here we can see we have three. numerical features as we already seen, and 9 categorical features. Okay, and we are seeing the proportions. So all these have like equal proportions. Okay, and for our continent, we can see Asia is the highest, 66% of data, 66% of rows has Asia as its continent. Then comes Europe, then comes North America, and like very less Oceania. For education of employee, 40% are of bachelors. Okay, and for case status, we can see 66% of 66% of them have been certified and 33% of them have been denied. So this is our imbalanced data. This certified is our majority class. This is minority. So we'll have to deal with it in the future. So these are the insights. Case ID, unique values for each column which can be dropped as it is of no importance. So case ID we are going to drop. Continent is highly biased towards Asia. Hence, we can combine other categories to form a single category. Okay. So this is another insight, and unit of wage seems to be important column as most of them are yearly contracts. Okay. So I think this is good. Now for univariate, so we are going to start our univariate analysis. As you can see, for our numerical features, uh, insights are that number of employees columns looks more skewed, but it is because there are a lot of outliers here, you can see. For years of establishment also it has a long tail here. Okay. So as you can see, year of establishment is a discrete feature. Yeah, it is a discrete feature, obviously. So most of them are around like 2000, but some of values are also 1800, 1850, as we can see here. And prevailing wage, it is a slightly right skewed distribution, as you can see, not normal. So these are our analysis. And for categorical features, we can see univariate analysis. For continent, the highest is from Asia, which we saw, and the lowest is from Oceania. For our education of employee, most of them have bachelor's, then comes masters, then with high school, and very less with doctorate degrees. For has job experience, most of them has yes. For requires job training, most of them has no. So these also make sense, both of them. Okay, and region of employment is mostly northeast and very less in the island. Unit of wage is yearly mostly. Some of them are hourly and rest are weekly. Okay, so these are denied, certified, etc., etc. Okay, so for this, like most of them are certified. For full-time position, most of them have yes. Okay, okay. So requires job training, unit of wage, full-time position, and continuous column have single category dominating. In rest of columns are balanced. So these are our insights, which we already seen. Now let's see the multivariate analysis. So check correlation in numerical features. So first we are going to check if there are some features correlated or not in numerical features. Okay. So as we can see, none of them have very high correlation, not at all, no correlation at all. So here we can see no correlation between any numeric variables. Okay, so now we have to check if our categorical features affects target variable or not. So we are going to do hypothesis testing for this. So our target variable is categorical and our feature is also categorical. So for that we have to use chi-square test. And so as you can see in our hypothesis, the feature is independent of target column, and the alternate hypothesis, feature and target column are not independent. Okay, so as you can see, we have done try to test for them, and our column is for continent reject null hypothesis. So that means it affects our target feature. Education of employee also affects our target feature, but this requires job training, does not affect our target feature. It fails to reject null hypothesis. So we have to accept the null hypothesis, which is the feature is independent of target column. So we are going to remove this required job training going further. Okay. So no null values as you can see here, and the number of features are this number of employees, year of establishment, and prevailing age. Okay. So these are the continuous feature because they have unique values more than equal to 10. So we can say these are the continuous features for, okay, these are basic. Okay, now we are going to start our analysis. So we are going to see our numerical features with our target feature, okay, by plotting them. So number of employees versus case status, and is it denied or certified. So you can see it looks almost similar. Okay, and we have also done the we like let me see. Yeah, okay, so we have further done, sorry, my bad. Okay, so visually it's not clear. We are going to hypothesis testing going forward to see if case status is affected by number of employees or not. For number of employees, this is box plot and this is histogram. So the same things, number of employees and case status, but this is histogram. So as you can see, most of them, like the data is very skewed because in number of employees we have like a lot of outliers, so it's not properly visible here. So we are going to rely on our hypothesis test for that. For our box plot for year of establishment and case status, and this is histogram for both. So first let's have a look at box plot. As we can see, like it looks similar in ranges, right? So there might be a possibility that year of establishment does not have any effect on case status. So we are going to see this going further. Okay. Here we can see denied count. Okay. Here we can see that our certified is more for every year, but it is also because our data has more certified instances than denied instances. So this is because of that, because of the imbalance of our data setup. So this is also not clear from this graph. So we will see in our hypothesis testing. But for now, let's see the box plot and histogram for prevailing wage and case status. So as you can see, the denied one has prevailing wage slightly lower. The median is slightly lower than that of certified. So this might prevailing wage might be affecting the case status. This is what it seems. Okay, and yeah, let's see. This is our numerical features which affects target variable or not. So we are going to see the hypothesis test, but we have already seen that our data of our numerical features is not normal. It's not Gaussian. So we can't use the t-test and test like that because those are parametric tests. So we have to use tests which are non-parametric. So like men Whitney test. Okay. So non-parametric test like men Whitney U test. Okay. So I have written this, and the same are the null and alternate hypothesis, and we are checking if our p-value is less than 0.5, 0.05, 0.05, then we are going to reject the null hypothesis. Otherwise, we will say we could not reject the null hypothesis. And as you can see, for all our these variables, it's less than 0.5, 0.05. So we are going to say that all of them are affecting our target feature, which is key status. Okay, so number of employee have many outliers which can be handled. Okay, year of establishment is left skewed, prevailing wage is right skewed. So these are the analysis, the insights from our uh, graphs that we have seen. Okay, there are no missing values. This also we have already done. The case ID column can be deleted. Case status column is target to predict, and in categorical column, feature can be made binary numerical in feature encoding. So all these things we are going to do. For here, we are not going to remove any of these number of employees, year of establishment, or prevailing wage because all of them have effect on our target feature. So let's visualize our target feature. For that, we have plotted a pie chart. Okay. And as you can see, 66.17% of them are for data has certified, others have denied. So it's imbalance here. Okay. So imbalance data are types of data where target class are uneven. So this is just a definition I have written of imbalance data, but you get the point, right? Okay, so now we want to see if our applicant continent has any impact on visa status. Okay, for that I have just grouped by our continent, and for key status I have found out the value counts. Okay, and then I have normalized it so that we get it in percentages and not actual values. Okay, so for continent Africa, we can see certified is most of them. For Asia, certified is most of them. For Europe, certified is here 79%. For North America, 61%. For Oceania, 63. For South America, 57. So the lowest difference that I see is in South America. There the denied percentage is higher compared to than in the previous values, which we have seen. Okay, so can from this we can see that if he's from South America applicant, then the denial possibility is more compared to all these okay other continents. So now let's see the continent versus visa status. So you can see what we saw in values. Now we can see it in graph that the denied for South America and certified for South America has the lowest difference compared to all others. Oceania is also in a similar lines. Okay, but for Asia, North America, and Europe, for Europe and Asia especially, the difference is significant between certified and denied. For North America, it's in between, not much difference. For Africa, there is certain difference, as we can see. Now let's see the percentage of certified for all the continents. So we can see that Europe is the highest, 79.2%. So if applicant is from Europe, more chances of him being certified compared to all others. And if from South America, uh, lowest chances of certification compared to all the other continents. Okay, so these are the report. As per chart, Asia applicants applied more than other continents. 43% of certified applicants are from Asia. This is followed by Europe with 11%. Highest chance of getting certified if you are from Europe, and followed by Africa. Okay, so these are the insights. Okay, does applicant education have any impact on visa status? So we can see that for our doctorate, our certification rate is the highest compared to all the others. Okay, so and where is the denied one? Okay, and you can see for our high school, the denied rate is highest. Hmm? Yes. So if you are from high school and you are applying, education is only high school, then very high chance that you will get denied. And if you are of doctorate, then very high chance you will get certified. Now let's see the education of employee versus visa status graph. Same things you can see in this graph. Okay. For masters, certified and denied is the highest, very high difference. But the highest difference is in doctorate. Okay. And for high school, it's just the opposite. Denied rate is more and certification rate is less. So now let's see the percentage of certified versus education of employee. In this video also, in this graph also, we can see for doctorate, 87.2% chance that he will be certified. Means he will be provided the visa. High school lowest. Okay. Now we are going to see previous work experience has any impact on visa status or not. Okay. So we can see that for previous person who does not have job experience, he is less likely compared to that if he has the job experience. Okay. Same thing we can see from this graph. Okay. If he has job experience, more likely to get certified. If he has less experience, if he has no experience, less likely to get certified. Okay, these are the insights, okay, 4 insights that we already have seen from the graph. Okay, now we are going to see if requires job training make any impact on visa status feature or not. Okay, so we can see it looks like values are similar. Okay, sorry. Certified for both is around 66, denied for both is around 33, 32. Okay, so I think there is not much difference here. So for graph also we can see the same thing. The percentages are, there is slight difference, but not too big of a difference. Okay. And also in our chi-square test, we have already checked that requires job training does not affect our this thing. Chi-square is more than 0.05, so we have already concluded that this required job training does not have any effect on our target feature, and our graph also shows the same thing. So uh, let's continue. Does number of employees employ have any impact on visa status? So this is where we have plotted the graph. Let me zoom out. Okay, so we can see that this looks very similar. The distribution for both is similar, but there are outliers in both the classes which need to be handled. So for now, we can't see conclude anything from this graph. Okay. All right. Here we go with values again. Unit of wage. We can see hour, month, week, and year. Okay. For year, all of them, it's like 60, around 60% of certified. Uh, sorry, my bad. Okay. So we can see for the hourly, the denied rate is 65% and certified rate is 34. But for monthly, certified rate is 61% and denied is 38. Okay. And these are also similar to month. But the hour one is like opposite. So if it's hourly, unit of age is hourly, then very, very likely that he'll get denied, okay, as compared to certified. So yeah, this is important. So unit of wage is important because it affects our case status. So you can see hourly is opposite and this one's okay. So for hourly, it's only 34% chance you get certified. For others, it's about 60%. Okay, does region of employment has impact on visa status or not? So yeah, we can see that for almost all of them, most of them have been certified and some of them have been denied. But for island, there is the least difference. So if you are from island, if your region of employment is island, then you are very likely to get denied as compared to all the other regions. Okay? So you can see from this graph also, for island it's the lowest, 60.3%, and others are higher than that. So if from island, you might get denied. Possibility is more. And okay, these are the insights. Does prevailing wage have any impact on visa status? And we can see the prevailing wage thing here. We have grouped by that, and now we are plotting prevailing wage versus visa status. So from graph, it's clear that both of them have like similar distributions, but all of them have like outliers. The wage has outliers, so we need to handle it first. But from the graph, the distribution looks similar for both. Now we are going to see the prevailing wage based on education. So what if our education degree has some effect on our prevailing wage or not? So you can say master's is like 78, bachelor 73, high school 71, doctorate it's like doctorate is 64. Okay, so this is sort of a weird because the most studied education where the education is highest has like the lowest prevailing wage. So yeah, as you can see, doctorate has the lowest and the highest is of masters. Okay, and the bachelor's is slightly higher than the high school. Okay. Master's education applicants have a median 78.8K, which is approximately 20% higher than doctorate's average wage, which is strange. Okay. So let's see if our experience has some effect on our prevailing wage or not. So you can see that if there is no experience, then it is 72,000. And if there is experience, then it's 69,000. So surprisingly, here also people who have less job experience or no job experience, no, not much job experience has more prevailing wage. So freshers are getting more paid as compared to those having some job experience. Okay. So this is also a weird pattern which we can see here. Let me see if my video. Okay. Okay. Prevailing wage based on continent. As we can see, Asia has the highest prevailing wage. Africa has the, what do you call, the mean is slightly lower than that of Asia. Then comes Oceania, then comes North America, South America, and Europe. Europe has the lowest prevailing wage. Okay, so as we can see, the same graph is shown here. So average salary of people from Asia is higher than other countries, other continents. Now let's see year of establishment. Year of establishment with our denied or accepted. Okay, with our prevailing wage also. So prevailing wage, year of establishment, and in hue we have case status. So here we can see that there is each bin consists of 5 years. Many companies were established after 2000, but some of them outliers are there for before 2000 also, as far as 1800. So this is the insight we have. And the final report we can say is case ID column can be dropped, requires job can be column can be dropped as it does not impact our target feature. Number of employees, prevailing wage columns have outlier which should be handled. Continent columns has few unique values with less count, which can be made as others. Target column case status is imbalance, can be handled before model building. Okay, so yeah, now let's see our next feature engineering and model training part. Let me see if my video is on. Okay, so let's continue. For our data pre-processing, so let's continue. Okay. So in this file, in this IPYNB file, we are going to do feature engineering. We are going to use the insights from our EDA. Okay. We'll drop the things, we'll handle the outliers, etc., etc. We'll do the pre-processing and we are going to train the model. And we are going to select a model which performs the best. Okay. So we are just importing this is data cleaning, handling of missing values, null values. We can see there are no null values here. Other data cleaning steps. Duplicate value is also not there. For feature engineering, feature extraction. So, okay. So now let's start our feature engineering. We will start with our date time. So we are going to take our today's date and we are going to store in here. So we are going to take today's date from date to today function and then we are going to take the year from that full date. We have year, month and date. Okay, in today's date. So from that we are taking year and we are storing it as a current year. Okay, so it's 2024. Now subtract current year with the year of establishment. So we'll get the age of company. Okay, so we have created this feature company age. And we are going to drop the year of establishment because we have used that already to create this feature. Okay, so type of features is okay. So type of features. So we have numerical features as three. This we have already seen. Categorical features we have eight. This we have already seen our EDA. Okay, for split. So now let's start the splitting process. First, we are going to drop the case status because it is our target feature. We only want to store our features in X. So we are going to drop that and we are storing that case status as a Y. Okay. So, and now let's see the manual encoding for our target feature, which is Y. So for denied, we are going to do 1. And if it is certified, then we are going to do 0. Okay. As you can see, denied is 1 and certified is 0. So we have done the encoding there. Now let's do some feature transformation. So we have seen that for our numerical features, its shape is not normal. It's skewed, as you can see here. Okay. So we are going to fix this. We are going to make this a Gaussian-like by using a power transformer feature-wise. Okay. Power transformers. Currently, power transformer supports the Box-Cox transform and the U-Johnson transform. Okay. So this is just I have written the definition of skewness, which we can already see from this graph. It's skewed towards the this side, the right side. Okay. So we want to fix this. Now we are going to check the skewness. We can see that positively skewed are company age and number of employees. Okay. And we can handle outliers and then check the skewness. Okay. So now applying the power transformer and to check if it reduces some outliers for us or not. Okay, so method we are going to use is Leo Johnson and the transform features are company age and number of employees. Okay. Here we have prevailing wage has very less skewness, so we have not included it here. But yeah, so we are fit transforming it and we are storing it in X copy. Now let's plot them. So we can see that it's more of like now Gaussian. Okay, so our skewness is fixed here. Now we can check that skewness is less than 1. So very, very low. Okay. And why we have used Leo Johnson and not the other one? Because Leo Johnson supports both positive and negative data for transformation. So we have used that one because we had, let me show you where is it. Okay, so it's fine, I think. I think the transformation is clear. We do not, I do not need to go into details of this for Leo Johnson. Okay, so now let's continue feature. Okay. For featuring categorical features, we are going to print the unique value. So continent has 6 unique value, education and prices 4. Same we can see for other things. Okay. Now let's do feature encoding and scaling part. So one hot encoding for columns which had lesser unique values. Okay, and they are not ordinal, so that means there is no inherent order there. So we are going to use one hot encoding for that. Okay, for ordinal variables which have some kind of hierarchy. Okay, for them we are going to here as a label encoder is supported for a column transformer. Okay, so we are going to do that for our ordinal variables. We are going to do ordinal encoding. Standard scalar, we are going to standardize them, and after standardizing we will have the values between -3 to 3, and all the features will be scaled. Okay, so selecting the number of features for pre-processing, number of numerical features is here. Okay, we are going to pre-process that using column transformer. So you can see I have all these pre-processing here. Numeric transformer, OH transformer means one hot transformer, and ordinal encoder. Okay, all of them are here, and we are storing it in a preprocessor. That thing. We are first using the column transformer, which is from sklearn.compose, and we are passing these values, okay, which we have defined here in here. So we in future when we are using that, we are creating this preprocessor object so that we do not have to do all these transformations separately when we do this in future, when we are making the deployment, the end-to-end part, where when we are making the components, we can just use this object, which is the preprocessor object, and it will do all the transformation for us. We do not have to do this separately, each one of these separately. Okay. So yeah, and we have created a pipeline which has the power transformer. Okay. Now we are going to use the preprocessor dot fit transform, and we are going to transform the X. Okay. And for preprocessor, we have already here object created, and we have used OH transformer for OH columns. So it will find the OH columns from our X, and it will apply OH transformer there. It will find OR columns from there and apply ordinal encoder there. Okay. So in such a way, we have easily transformed all our features at once. Okay, with this one line of code, and you can see the transforms thing is here. For classification, we are first going to use motenn because we want to balance our imbalance data set. So there's an oversampling method. So we are going to use this. Minority class will be increased equal to the majority, so that both of them matches and the imbalance is gone. Okay, so this is just that, and here we are storing the X rays and Y rays after using smart NN. Okay. So I think this is simple. Now we are going to do the train test split. We are passing X rays and Y rays. 20% is for test and rest for train. Okay. So now we are going to assemble all our models. Models which we want to use. I have just imported it here, and you can see random forest, ADA boost, gradient boost. logistic regression, KNN, decision tree, SVC, and these are the metrics for our classification. XGBoost also we have used, GetBoost also we have imported. So now what we are going to do is we are going to first write a function that will give us all the matrix, okay, performance matrix here, and we are going to return all of them. So for each of this model we have written, we have to first fit it, and then we have to just use this evaluate CLF function. We have to pass the true and predicted values, and it will give all the performance metrics to us, so that we do not have to write this again and again, precision score and all this. We can just use this function and we can get all our performance matrix. So that is why I have written this function. Models, we can see all the models are here. Okay. Uh, I have stored it in models, and now we are going to write a function which is evaluate models and return a report. So this function is for that. It will take x, y, and the models list, models dictionary that we have created. First, it will split, and this is for storing our models accuracy list of models and the AUC. This is empty list. We are going to fill this, and we're going to return this going forward. So we are taking the list from the did I do anything bad? Okay, no. Okay, so we are taking the length of from the list of our models, and we are going to iterate it, and it will take one by one. It will take model one by one, and it is going to fit it, and it is going to get the predictions, okay, and then it is going to pass it into evaluate CLF, and then it is like going to get our this all the performance metrics, okay. And after that, okay, this is for training. Okay, so we are going to train, and we are going to get the predictions from our train, storing it in y train pred, and from prediction from our x test, we are going to store in y test pred. Okay, and then we are going to pass that for y train and y train pred. We are going to get all the matrix, performance matrix for a training set, and here we are getting all the matrix for our testing set using our evaluate CLF function that we have written already. Okay, let me see if the recording is on. Yeah, it's on. Okay, so now models list, we are appending all of them. Okay, and we are going to print our that thing, and we are going to give a report at the end. Okay, which will create our zip for models list and accuracy list, and it will give it as a list where the columns will be model name and accuracy. So what we are doing is we are storing all our that thing accuracy for our model. For each iteration we are using each model. Okay, so we're going to store that model name. We are going to get store the accuracy we get from after that. After testing that model, we are going to store return it in our report, okay, as a form of a list, and then with all this list we are going to convert it into a data frame. So what we'll get at the end is a data frame, okay, which will have the model name and the accuracy that that model bring for all our models. Okay, so I think this is clear. Now we are going to use the run this evaluate models, and we are going to see the base model report. Now let me open this report. Okay, so we can see for training set it's like 1 1 1 1 1. So this is like overfitting the training set, but for our test set it's 95 95 95. Okay, so I think this is good. For decision tree also training 1 1 1 1 1. For our validations test set it's 93 92 92. Okay, so such kind of things. For our gradient boosting, it's like 88, 89, 89, and this is 89, 90, 90, 90, 89, 89. Okay, so these are like this is closer to each other, so this is not that overfitting. This is good, but let's see if there are better ones. This is logistic regression, the simplest one we have used. So you can see not that good accuracies anywhere. For KNN, the accuracies are very good. Like it's like not one, so it's not overfitting clearly. For training, it's around 96, 95, and for this thing, for test is also around that range only. So we can say this is not a overfitting. This is a good accuracy, good model. KNN perform good. For XGB, you can see also like similar things perform good. XGB, cat boost also good. Accuracy is less compared to previous ones, but okay, not overfit. This accuracy is bad here. SVC compared to others. Okay. For EDA boost also not that great. Not in 90s. It's in 80s. So not that great. Okay. So we're going to see. Okay, now I have printed that data frame which I talked about. You can see random forest is the highest accuracy, then comes the KNN, then comes the XGB. So we are going to use these three models, or rather we are just going to use these two models in our upcoming when we are deploying, when we are writing code for all the components. We are going to use these two models. Okay, so now let's just do some hyperparameter tuning for this. Okay, we are going to use the that thing grid search. Okay, you can see I have given range here. I have given range here. This is XGBoost parameters. This is RF parameters. This is KNN parameters. So I have used the first three models, best performing models. I have used the parameters for them, and I have given the random created a object, a list rather, in which I have stored the XGBoost name, the model, and the parameters. Okay, and I am passing that. Now we are going to create a function for model training and report, which can be used in hyperparameter tuning loop. Okay, so from random CV models, we have three things stored, three things there: name, model, and parameter. So we are taking that here. Okay, in loop. We are using random search CV as I told you, giving estimator as model, parameters as params, and iteration I have given 100, CV is 3, and verbose is 2, and number of job is -1. Okay, so CV means it will split like three parts, two parts for training, one for validation. It will train on these two parts, check the performance on validation, and for all our hyperparameters, so whichever performance of validation is the highest, that number of hyperparameters will be returned to us as the best hyperparameters. Okay, so you can see all this training I have done, and now you can see the best parameters is this. Okay, for RF it is this, for KNN it is this. Okay, oh, sorry. Okay, so now interesting. Now we are going to use these parameters and we are going to store it in best models. And then we are going to do the evaluate models thing, and we are going to have our report which will show us the performance of all our three models. So you can see our random forest is like 1, 1, but our test set is 95, 95, 96. So it is good. For our KNN, it is around 1, 1, 1, 1. But our accuracy is 97, which is highest than this one also. For XGB is 99, 99 for training, and for accuracy 94. So best accuracy for our test is in KNN. So it is by far our best model here. Accuracy is 97, and we can see that accuracy of KNN is highest, 97, and we can see that our best model is a KNN, and this is the confusion matrix for that, where F1 is 0.97, F1 for 1 is 98. So yeah, this is good. This is our confusion matrix, and our best model is KNN with accuracy of 97%. So yeah, So this was our notebooks, the initial part of our project. In the next part, we'll start all our components of pipeline till deployment. Okay, so stay tuned. Bye.